Hi, I'm Arya. I'm a computer science grad student at UC Santa Barbara, and I'm going to be talking about how we're working on a model to diagnose Alzheimer's the Bayesian way, and this is joint work with Ben Bales and my advisor and Michael Harrington, who's a neurologist we work with. Okay, so imagine you're sitting at home at your desk and downstairs a fire starts. And you don't realize it yet because it's small, but if it keeps going, it'll burn down your house. And now imagine that outside the firefighters are driving around making sure all the houses are all right, and they stop by your house and they take a look and say, well, we haven't checked the CO2 levels, but let's mark it as fine. We don't have to come back for a while. It looks fine. And eventually you're going to be in trouble. And now imagine the reverse scenario where you're sitting at your desk and this time there's no fire, but you decide to make some tea. So you turn on your kettle and it starts steaming and filling up the whole room. And this time the firefighters drive by and they say, whoa, look at that, it's smoking, and they halt the truck and they get out and they go up to your door and they kick it down, and the fireman comes in and he looks at you and he says, oh, false alarm, he's just making tea and reading the Gelman blog or whatever you're imagining yourself doing. And the problem with this is that they could have been saving other people who needed it, and now their resources are going to cost the city a lot of money, or if you've been imagining yourself in the US, it's going to cost you a lot of money here. And the reason why this is important is because Alzheimer's disease is ranked the most debilitating disease because unlike a lot of other diseases, it primarily targets the mind. Patients experience memory loss and trouble remembering loved ones. They have trouble performing daily functions like eating or bathing, and they experience worsened moods like depression and anxiety. And the bright side is that we can help these patients now, but only if we can diagnose accurately. So there was a study done where they took about 1,000 senior citizens and they wanted to see how well Alzheimer's was being diagnosed. And it turned out that 11% of patients had Alzheimer's, but they were misdiagnosed as being healthy. So these people missed out on possible early interventions or drugs that could have helped their memory. So this is like the people in the house that the firemen skipped out on. And then you have another 11% of patients who were healthy, but doctors thought they had Alzheimer's. And these are the people who are fine, but the firemen kicked down their door anyway. And these people end up costing $14,000 a year, according to one study, when they don't even have the disease. And additionally, new drugs are constantly being developed, but we need a way to recruit the right patients for studies on these drugs. And the reason for these errors is because diagnosis is currently done manually, and it's imprecise and subjective. And the way it works is that physicians take and examine what are called patient biomarkers, which are things like blood tests, verbal memory tests, or MRI. And in healthy patients, these biomarkers tend to hover around some healthy value. And in Alzheimer's patients, they're usually at some lower unhealthy value. And as the disease progresses, they kind of slide down to that unhealthy value in that logistic shape. But the way diagnosis currently works is that physicians look at these biomarkers and they place patients into one of three categories. healthy, mild dementia, and dementia. But the problem with that is that, first of all, it's too imprecise for a disease that we believe to be evolving continuously. If you're in one of those edge cases of the 3 classes, how do we know how to treat you? The other problem is that they're only looking at a single snapshot of these patient biomarkers, and there's so much temporal information there that could tell us about the nature of a given person's disease. And lastly, this is subjective, so it's going to be prone to inconsistency. So what I want to argue is that we need to diagnose the Bayesian way. We need a generative model to describe how Alzheimer's and biomarkers progress. We need uncertainty estimates of a given patient's disease progression, and we need multi-level models because every patient is different. So to understand a complex process like Alzheimer's progression, we need complex generative models. So like I said, patients are going to have these logistic-looking biomarker curves that are all kind of degrading simultaneously, and what's driving this is the kind of the degradation of the brain and the progression of Alzheimer's disease itself. And so one of the ways this has been modeled by Jedinak is using a disease progression curve for each patient, and that's just going to be a function that tells you an individual's disease severity given their that patient's age. And that is sort of a latent variable that's going to drive these biomarker observations through a 4-parameter logistic function that's specific to each type of biomarker. And at this point you might ask, well, why don't we just use classification to figure out which of those 3 categories these patients fall in? And one reason is that, well, those classifications are noisy, and again, they're not precise enough. But a bigger reason is that doing a generative model is going to advance our understanding of the disease more so than simple classification. And the way that happens is through these intricate disease progression curves that we capture that are going to tell us about different patterns in the way the disease evolves. And through these logistic parameters that accompany each type of biomarker. So for example, that gamma term is an offset that determines when those logistic curves start, and that'll be informative in knowing which of these we can expect to start showing up in patients first and relative to when the disease progresses. And that beta term will tell us how fast we can expect these biomarkers to start regressing once they do. And the other reason we want to use a generative model here is because a model represents our understanding or knowledge of some bit of science. So we can expand our model, and that's going to tell us when our understanding of the process we are modeling is too simplified. So I haven't talked too much about it yet, but one of the ways we can model those progression curves is using linear terms, or we could use something more general like a nonlinear monotonic spline. And when we go and fit these 2 respective models to data and see to the same data, and we see that a patient has progression curves that are nonlinear, that's going to tell us that, well, their progression is nonlinear. And knowing those kinds of things are important and something physicians value. For example, that step-like pattern that we captured there in STAN, that is characteristic of a type of dementia known as vascular dementia. And then the other reason we want to use generative models is because we can simulate from them and compare our simulated data to our real data, and that's going to tell us when our understanding is wrong. So I talked about how we have those biomarker, how we have this biomarker distribution, and we have that sigma j term that's kind of saying the variance of a given biomarker is the same across all patients, so that like a given patient's day-to-day variance in their MRI will be the same across all patients. And when we went ahead and fit and simulated from that model with the simulated data in orange there, we saw that that wasn't necessarily fitting our data. Sometimes the variance was too large in the first two cases in the upper left, and sometimes it was too small. So that told us something interesting, which was that different patients exhibit different varying behavior on these tests, which was kind of a cool insight. And so the other thing I want to talk about is why we need uncertainty. And the first reason is that it's crucial in guiding treatment. So these posterior disease progression curves represent the possible paths a patient will evolve in given their observed biomarkers. So if we know a patient has a low risk of progressing quickly, like the patient on the left here who doesn't have very many paths where they go to a really high disease severity, then we can be more cautious about administering new drugs that may have potential side effects. And the other reason we need uncertainty is because we need to be able to make statistical claims about drugs and other interventions. And that's going to be really easy in the STAN MCMC framework. If we have B representing the disease severity path of a patient who takes a drug, and then A representing their path when they don't take a drug, we might want to know, is B going to be less severe than A at some future time t? And that probability is just an expectation that we can compute simply in STAN. All we do is go to our generated quantity blocks and generate that trajectory when the patient doesn't take the drug and when they do, and we just compare, is that severity less, and do that over and over for multiple samples. And the way we capture the uncertainty specifically in our model is with something called I-splines, which are these monotonic increasing basis functions of splines, such that when you take a linear combination of them that's constrained to be positive and constrained to sum to 1, you get these curves in black, which are themselves monotonically increasing. They start at 0 and end at 1. And then if you have data from such a process, it's simple to infer something like this in STAN. You just set up a little simplex parameter representing the linear combination. You evaluate the I-splines, which I have some code to do online, and you do a simple vector matrix multiplication. Okay, and lastly, I want to talk about why we want to use multi-level modeling on this sort of data. And the reason is that no two patients have identical trajectories. So everyone is different, and we're going to want to use unique I-spline coefficients for all of them, and but we want similar patients to be informative of one another. So you all know where I'm going with this. It's that we need to place hierarchical priors on those coefficients to borrow information when data is sparse. And again, that's simple to do in STAN using Dirichlet prior on those linear combinations.
Very interesting talk. I should say a few things. I work for a company that's been developing disease progression models for Huntington's disease for years, actually. And so this is relevant very relevant to our work. My main question here is, what are you using as the x-axis for all of those curves? In Huntington's disease, we have something called it's a neurological disorder with a known, very strong genetic effect. So we combine age with a genetic marker in something called the CAG age product there. I'm curious as to what you and using age alone doesn't work very well. I'm curious as to what you use on the x-axis in these models.
Well, so we have age on the x-axis for the latent disease severity. So for a different patient, their disease severity might be higher or lower at age 60 or what have you, and that's going to capture those individual effects of people progressing to worse or less worse disease severities depending on their age. And that latent function is then what drives the biomarkers that we actually observe. Does that answer your question?
It begs the question as to exactly how that latent variable is calculated. But I think that makes much sense.
Through the data, so this orange data is actual observed biomarkers, and that's going to affect the shape of the sigmoids, and then the sigmoids is what affects the shape of the I-spline.
All right, there's one last question, and then we'll switch over laptops.
Hi, thanks for the talk. Similar question in vein with how well do you trust your measure of disease severity in regards to Alzheimer's as does they have a yes no?
That's a good question, and I think my answer would be we trust it insofar as we can faithfully regenerate the data. I think if we have posterior predictive simulated data that matches our real data well, then we can trust the process, so to speak. And I guess another way to check that would be to hold out patients and see how well we predict their trajectories.
Okay, thank you.